All right, here's third time I've tried to actually record this. First couple of times my cat was giving me issues, and the last time I got an alert about an email from Mrs. Tibbs that really nobody needed to see. You know what I'm saying? So here we go again. Well, here I go again. Here you guys go for the first time. Talking about systems of equations. Hopefully you have looked at that video that I uploaded last week. I really like that guy's channel. If you are at all interested in math and science, I would say, or science, I would say his stuff is worth watching. But he gives us a good idea of why we are even talking about systems of equations, why we bother solving them algebraically or graphically, and what's happening in 2 and 3 dimensional space. And it's kind of fascinating, especially when you start talking about, you know, a 4th dimension, or when you start looking at systems of equations in, you know, 5, 6, 7 variables. It's pretty fascinating. Okay, you just take my word for it. I know you guys are all about calculations. You like solving stuff. This particular group loves that stuff. So you should love systems of equations. And we'll be talking about these for the next, well, all this week at least, possibly into next. Okay, so 3 ways to solve systems of equations that we're going to talk about. We may circle back to Kramer's rule when we start talking about matrices, but for right now, the primary, what you guys need to be concerned about is solving by graphing, substitution, and elimination. So graphing, as you can see, I have my little and I have circled where the graphs, the lines cross, and where they cross is the solution to the system. So the solution to a system, we're just talking about a solution to each equation. It's the one solution that satisfies each equation. So of course we're talking about a point that is on each line, and that one point is where they cross, and I have, I think I decided that was 3, 1. I've sort of obscured that with my circle. And solution to a system of equations is going to be written as a coordinate set. So we have, in this case, 2 equations, right, with 2 variables, 2 unknowns. We're going to have a solution set with 2 numbers, right, a coordinate pair. When we get into systems with 3 variables, we will have a set with 3. Okay, so that's graphing. That's all there is to that. You just graph the lines the way you know how, any way you know how. You can use standard form and x and y intercept. You can rewrite it in slope intercept form. Whatever works for you. Get the lines on the page, and where they cross is your solution. Now, understand that there are systems with no solution. Those would be parallel lines. And there are systems with infinitely many solutions. Those would be equations that turn out to actually be equations for the same line, right? They overlap, and lines are infinite. You remember from geometry last year. Okay, solving by substitution. Again, this should look pretty familiar. So I'm going to call that equation 1, call that equation 2. And I'm going to rewrite equation 1 as it is. Just going to copy it over here. And rewrite this equation for r in terms of s. I'm going to use that expression in the first equation. So I'm going to substitute s plus 8 for r in the first equation. 2 times s plus 8 and get s equals -5. Easy stuff, right? Kid stuff. But I still need to find r, so I'm going to substitute -5 in for s, again in the first equation. Doesn't have to be, by the way. Just what I'm going to do. So 2r minus 5 equals 1. I'm going to write my coordinate pair in alphabetical order and get 3, -5. I have to make sure that this is actually a solution, that this point is on both lines. And the only way to do that is to substitute both of these values in for r and s. And I'm actually going to do it in the second equation. I'm going to do my check in the second equation because I actually used the first equation, right? I used this equation to find r. So I know that this coordinate pair is going to work in that equation because that's the one I used to find my numbers. So I'm going to substitute 3 and -5 in for the original equation. Should always be substituted back into an original equation. And I'm going to use the equation I didn't use to find those numbers. So r, I have 3 minus a -5 should equal 8. And oh, look at that, it does. So that's what's up there. Kid stuff, right? All right. Let's do one more. Again, this we get 3x plus 2y, and I want you to see this one because I want you to get used to the fact that you're going to have some funky answers. I'll rewrite the second equation again. Y in terms of x, just get rid of that negative. You could actually write an equation for x in terms of y, but this makes more sense, right? So substitute back into the first equation, 3x plus 2 times x plus 2 equals 8. Yuck. Fractions. All right. Well, let's just plot ahead and see if this works. So I'm going to use, in this case, I'm going to use the second equation to find y. I get 4/5 plus 2 equals 2 4/5, right? Tricky. I like improper fractions for a lot of reasons, none of which I'm going to discuss here. 10 plus 4, 14/5. I happen to know that this is, in fact, a solution to this system, but I will leave it to you guys to check, because you know how Ms. Polson likes, there we go, to have you guys check your work. Okay. Aww. Solving by elimination. Anybody remember this? So what we want to do in this case is very much like substitution. I mean, in both cases we want to get our two equations of two unknowns. We want to eliminate somehow one of those unknowns, right? Because we can't solve two equations for two unknowns without eliminating one of them. And up here we just write one in terms of the other and substitute. Down here for elimination, we're going to actually add these two equations algebraically in some sort of way that's going to eliminate one of the variables. Well, it just so happens that this is written such that we have a -3x down here and a 3x up here, and if we add these, they're going to eliminate, right? We lose the x. Add -6y plus 5y, we get -y. And 15 plus -8 is 7. Y equals -7. Okay, well let's substitute now this value, -7, into one of the original equations. I'm going to use the first one, and I'm going to get rid of this splotch here that looks like, oh, are you kidding? So let's do it in the first equation. 3x minus 6 times -7 equals 15. What is this going to give me? 17? 27. X equals 9. Why isn't this writing? There we go. So my coordinate pair, if I've done my math right, is -7, -9. We have to check. Let's use the equation I didn't use to find x, which would be the second equation. -3x negative 3 times -9 plus 5 times -7 equals -8. What is this? Plus 27 minus 35 equals -8, and that checks out. Okay, so what I want you guys to do in your notebooks is solve this one. Solve this last problem using any method. Now let's go through it. I changed my mind. So what is, oh no. What is the method that we want to use? Do we want to graph it? Do we want to use elimination? Do we want to use substitution? I mean, those are some pretty ugly numbers, right? Somehow, some kind of way, I feel like I'm going to end up with fractions. So, pick your poison. I think in my choice,